As Rafik mentioned, so today I'm going to talk about the larger scale traffic simulation applications and estimating NFD and trying to find some interesting observations for different applications of NFD or MFD. So this is the outline of my presentation, a brief introduction to the topic and also a brief background on the NFD and the particular topics that I'm going to cover. The modeling framework is basically the definition of the NFD, the typical definitions that have been widely. And then we are going to jump into 3 different applications that each of them are separate paper. I try to kind of combine them together and align them for this talk since they are kind of relevant to each other. The first application is regarding the NFD and network partitioning based on NFD and its impact on the reliability relation estimation. And the second one is regarding application of NFD in estimating a macroscopic model for emission estimation. And the third is regarding the application of NFT to assess different market share penetration of connected and autonomous vehicles at a larger scale network. And at the end, we're going to present some concluding remarks and, more importantly, some future research directions that we are following right now. Why we need transportation network modeling? I think the answer is kind of clear for everyone here. We have growing challenges of mobility and accessibility, specifically in large cities, where we have limited space and a growing demand because of the trend of urbanization that we are following right now in our lifestyle. And as a result, the congestion is growing, and there is not much space available, obviously, to expand the networks, specifically at the central part of the networks, which calls for developing strategies to combat this congestion. And to understand to kind of combat this congestion issue and problem, we need to consider the different components that is associated with transportation network. So we have travelers, we have supply network, and the travel demand as the 3 major elements of and components of the network modeling. So basically, travelers travel in the supply experience. Based on that, they would adjust their decisions, and that would compose the travel demand. And then the travel demand would be implemented on the network supply, and then again the travelers would have new experiences, and this cycle is going to go till we reach out to something that we typically call user equilibrium. And at that point we would have some network-wide performance measures, and the system planner is trying to affect the network supply and the decisions that travelers make to change the travel demand as is resolved to improve the system and come up with a modified performance measure. This is where basically the NFD, Network Fundamental Diagram, or also known as Microscopic Fundamental Diagram, is come to play to assess and evaluate these performance measures at the network level, particularly for larger scale policies, not for just localized improvement that we do in terms of congestion improvement, but what we do as kind of a larger scale policies that we apply for our networks. So the key research questions that we have here is to explore the network-wide estimation of travel time, reliability, and emission production and impacts of connected autonomous vehicles. And we would incorporate the NFD as a tool to monitor the traffic dynamics, and also use a simulation-based dynamic traffic assignment tool to estimate NFD. So basically, to explore those impacts, we are going to use NFD, and to estimate NFD, we are going to use a simulation-based dynamic traffic assignment tool, which is basically DYNASMART, developed by Professor Mamdani over the last 30 years, I would say. So first, a brief background on the topics. So the first earlier network level works go back to 1960s, and Godfrey was one of the first studies in 1969 that observed a non-monotonic relationship between speed and flow at the network level. Herman and Prigogine, I don't know why the names here. I apologize for that. So they developed a two-fluid theory in 1979. And in 1984, Macroscopic et al. Presented the network-wide relations between flow density and speed. They observed via simulation. In 1993, they observed the hysteresis phenomena. And ultimately, for a couple of years, there wasn't any active research in this domain until in 2008, the NFD concept is really theoretized and called Macroscopic Fundamental Diagram. And the study by Dagens and Gerolimus was kind of one of the prior studies in this field that kind of snowballed to other studies, many different studies that have done in 2010s during the last decade, and various problems have been studied. Here, some categories of the studies have been done. So certain studies were focusing on estimating the NFD. Three approaches have been used for that: analytical methods, simulation-based approach, and empirical studies. I personally have done lots of simulation-based approaches for estimating NFD throughout the years and observing different phenomena using NFD. Also, in addition to estimating NFD, along with that goes with the applications of the NFD, significant applications in the perimeter control, and more recent studies on the macroscopic dynamic routing. So basically, to avoid the computational deficiencies of simulation dynamic traffic assignment tools, we are willing to move on to the more macroscopic approaches, but we want to capture the dynamics of the network as well. So NFD or MFD provides a great opportunity for that, and there are many studies on that, say, during the last 3-4 years. And in addition to that, right now, multimodal NFD is another approach that we are looking at. Again, back to the limited space that we have, maybe shifting from passenger cars to buses could be an option. So there are certain recent studies on the multimodal NFD as well. So with that, we are going to jump into the 3 different topics that we have and provide a really brief background in each of them. So the microscopic simulation, empirical data, and also simulation-based dynamic traffic assignment tools have been developed during, again, last 10 years to study travel time reliability. One of the approaches were to capture a network-wide travel time reliability measure, which have been observed via NFD in multiple studies, as you can see here in this slide. So one of the major things that we felt that, so NFD, the homogeneity of the network, is a key component of NFD. And once we are dealing with the heterogeneous network, there are certain studies working on partitioning network to more homogeneous subnetworks. And one of the major things that we want to study here is that how this network partitioning and having more homogeneous NFDs would affect the travel time reliability relation estimation. In addition to that, and a kind of different topic in terms of the emission estimation, we have the microscopic modeling as one of the approaches in this domain, that there have been lots of studies there, and also there are packages ready already for that, CMA and MoveLive. And on the other hand, we have the macroscopic emission models as well, and there are certain tools developed for those as well. The issue with the microscopic model is kind of similar to the issue that we have with traffic simulation, is that they are resource intensive and they cannot be applied for the larger scale networks. And the major issue with the macroscopic models is that they are ignoring the vehicle dynamics, traffic dynamics basically. significantly. So one of the earliest studies related to the study that I'm presenting today is a study done by Sharikhan and Gonzalez in 2013, where they try to kind of relate the NFD with the emission estimation, but it's simple, the ideal ring model for basically intersection control concept. So now we would like to revisit that concept, but apply for larger scale urban networks. And finally, the third applications that we are going to cover is about assessing the CAV's impacts at the transportation networks. So at the segment level, there have been lots of studies in this domain, and most of them applying the microscopic simulation. But at the network level, there are a few studies that have been done. I've listed 3 of them here. And still, there is a need to consider certain elements in the evaluation of the CAVs at the network level, considering the mixed traffic, combining of the regular vehicles. I know that RVs might be a little bit misleading, so with the truck and van and RVs, but here we are referring to regular vehicles, and CVs refers to the connected vehicles, AVs refers to autonomous vehicle, and CAV stands for connected and autonomous vehicles in terms of terminology. So considering a mix of these different vehicle types during the transition period from regular vehicles and conventional vehicles that we have right now towards a fully connected and autonomous system, there is going to be a transition period, and it's important to capture network characteristics during this time. And we would have heterogeneous drivers in terms of the regular drivers and also regular vehicle drivers and also connected vehicle drivers. So we need to consider that factor as well. So as I mentioned, the NFD definitions that we are using in these studies are basically the QK relation. Q stands for flow, K stands for density. There are other forms of NFD, trip completion rate, and network accumulation is another approach to observe NFD, which they're directly correlated to each other. And one of the key important factors in defining the average flow and average density over the network is to calculate the weighted average. There were some early studies in this domain that they ignored this fact. And I recall when I was a PhD student, I was trying to define an NFD, and the shape and everything was not well defined if you do not do this weighted average. So it's important to calculate the weighted average, and it shouldn't be just based on the length. It should also cover the lane as well. So the number of length of the links play an important role to capture the average flow and average density in the network. So the other part, it's part of modeling framework that I would like to talk about is regarding the definition of the travel time reliability relation. So it has been observed by applying the simulation-based dynamic traffic assignment tool that you can define a relation between the mean travel time and the standard deviation of travel time. So once you know the mean travel time, you would be able to estimate the standard deviation of travel time as well, just using linear regression models, or different models have been tried, but at the network level, basically the linear model shows promising results. But one of the key elements here again is that the travel time needs to be normalized by the travel distance. So the mean travel time per unit of distance is kind of linearly related to the standard deviation of travel time per unit of distance at the network level. And as you can see here, the relations are mentioned here. So we have defined T prime, which is T over D, which is kind of pace, invert of speed. And then we have the weighted average again based on the distances between different links that we have over the network to calculate the mean travel time. And also again, the weighted average over the deviations from the mean value of the travel time per unit of distance to capture the standard deviation. And ultimately, we have the standard deviation related to the mean travel time per unit of distance, and we have two factors that needs to be estimated as the coefficients of the reliability relation. So with that, we are going to go to each study for now, and then ultimately we are going to come back all together and talk about the future studies that can be done that would relate these three different applications to each other. So for the travel time reliability analysis, the main objective is to improve the reliability estimations, incorporating the NFD. In that regards, we need to apply the partitioning techniques. To apply the clustering, we have defined this objective function here. It's a time-dependent clustering approach rather than just doing it for one particular moment and just follow that clustering that is given by that one particular steady state of the network. Instead of that, we are considering the dynamics of the network throughout the time in defining the clusters. That was one of the contributions that we did in this study. As you can see, the KJT is the density of the link J at time interval T. And we define an average density of the cluster I at time T as well. Basically, the major decision variable that we have here is to determine which link J should be assigned to which cluster I. So if you know that we have a known number of clusters, then we would be able to allocate the links to the different clusters in a way that we would minimize the deviations inside each clusters and maximizing deviations between the clusters. So one of the things that needs to be considered here is that the clusters should be defined with certain constraints in a way that the links that belong to the same clusters, they would be all connected to each other. So we wouldn't have kind of some islands of the links that would conform the same clusters. So the connectivity is an important issue to be considered. And in addition to that, we explored two different types of clustering approaches in this study and compared them, the directional versus the non-directional one, which is kind of coming from the basic understanding of if you have a two-directional link, bidirectional link, two directions, two different directions, should they belong to the same cluster or not? So the directional approach is where we are relaxing that constraints. We are saying one direction could belong to one cluster and another direction could belong to the other cluster. In the non-directional approach, we are finding a constraint, an additional constraint. We are imposing if one direction belongs to the one cluster, then the opposing direction should also belong to the same clusters. They cannot belong to different clusters. Again, there is no right or wrong in my understanding for this assumption. There are just simply two different assumptions that you can make. In one sense, it makes sense to have both directions belonging to the same clusters because they are in the same location. However, we know that we have directionality of flow, specifically during the PM peak and AM peak, they might be exactly opposite of each other. So because of that, if we are just studying for PM peak or if we are just studying for AM peak, it's kind of making sense to consider that directionality in defining the clusters. However, if you're defining them throughout the day, you might be able to relax that. But again, there is no right or wrong. There are just two different approaches that we are gonna. In terms of the travel time estimation, there are two methods applied in the literature, the trajectory-based and the sub-trajectory-based. So the methods are not developed in this study, but what we did is that I think it's for the first time that we are comparing these two approaches. They both have been done in the literature, but no one has compared these two approaches together. And basically, in both approaches, once we want to estimate the travel time reliability relation, so As you mentioned, we have the mean value and the standard deviation. So we need to define a set of observations, basically, then calculate the mean value and the standard deviations over those observations, and that would give you 1 point, correct? So for certain time interval, you have one mean value and one standard deviation value. That would be one data point that you would have. Then in another time interval, you would have another observation, another mean, multiple mean and standard deviation throughout the simulation horizon, and then you would be able to estimate a regression model, simple linear regression model, to calibrate the relations that we already defined. Usually consider 5 minutes time interval, and every 5 minutes would give us one data point, and then we would be able to estimate the reliability relation. And that has been done in the literature, as you can see, the trajectory-based approach and the sub-trajectory-based approach. However, the way that we can define the segments that would determine the mean and the standard deviation for each time interval is different in these two approaches. As you can see here, so the trajectory-based approach is that if you have a trajectory, a vehicle trajectory, so this is basically the simulation time, this is the travel distance, this is the 5 minutes segment that will give you the one data point of mean and standard deviation. For that, you need to have multiple segments that you would calculate the average value and the standard deviation over. The key here is that, so for these 5 minutes interval, you might have trajectories, the vehicles that would start their trip during that 5 minutes and continue their trip beyond that point. And you could have trajectories that have already started earlier, and during that 5 minutes, they're traveling around the network, and they will continue beyond that as well. Or you can have trajectories that they will get to their destination during this 5 minutes interval and generated earlier. So now the key is that what portion of these 5 minutes of these trajectories am I supposed to use to estimate the mean value and standard deviation? Again, there is no right or wrong. You could have two different approaches, which is the trajectory and sub-trajectory. As you mentioned, they both have been done in the literature. So in the first one, in the trajectory base, is that if a trajectory is originated in that 5 minute interval, then we would consider the entire trajectory and would associate that entire trajectory observations for this 5 minutes interval. So basically, the definition is coming from the generation of the trajectory. And it continues till the end of the trips, right? And for these ones, they have already been captured in the previous time interval, so they won't be counted anymore because they have not been originated in these 5 minutes intervals. So in this case, you would have the travel time for this trajectory. You have the travel distance for the trajectory. You divide the travel time by travel distance. You get the travel per unit of distance. And that would be one data point. And then you would have multiple trajectories generated in that 5 minutes. Then you would calculate the average. That would give you one mean value. And you would calculate the standard deviation among those. And that would give you one standard deviation value. In the other approach, which is the sub-trajectory approach, is that we are focusing on the actual travel that network experienced during that 5 minutes. So for that case, you don't care when the trajectory is generated. If a vehicle trajectory is traveling in the network during that 5 minute interval, you would just capture that 5 minutes of trip for that trajectory, which might be less than 5 minutes. Not necessarily the travel time would be equal to 5, because it might have been generated in that 5 minutes, so it would be less than 5 minutes, and the distance would be whatever is associated with that. And for the other ones which have been generated earlier, we would have the travel time equal 5 minutes, and we would just divide it by the distance that they have traveled in that 5 minutes interval. And then we would calculate the average between these values and also the standard deviation, and that would be one data point. Then we would move on to the next 5 minutes interval that would give you another data point to be able to calibrate the linear relation. So basically, to observe the impacts of the network partitioning, we considered a larger scale network. As you can see, we have the Chicago metropolitan area network, which has been simulated, and 40,000 links, 30,000 nodes, 2,000 zones. This is the demand profile that we have for the entire day. as you can see. So we have some base demand that would be always populated the network even during the I think this is the midnight, so this is kind of early morning. This is again late in the night. This is kind of the base demand that we have over the 24 hours. This is the AM peak, this is the PM peak, but to be able to apply the net partitioning algorithms and also to have a better sense of the congestion, because this network is really large and there might not be much congestion around here. So we decided to just focus on subset of this network, as you can see here, which includes about 10,000 links, and perform the clustering approach for that. And to just give you a scale, this is what you can see here in this part is just the CBD or Central Chicago downtown area, basically. We should call it loop as well. So this is the study area that you are trying to estimate the travel time reliability measures and also perform the clustering or partitioning. So this is the simulation result. So this is just showing the results for the AM peak, PM peak, and the off peak period between. So as you can see, the network is getting congested, gets the maximum flow, contains the maximum flow for a while. Then we have an unloading. As you can see here, it's kind of standing for this unloading demand here, come down, and then we have the off-peak period here, and then again, it's gonna, so basically this portion here, and then after a while, it's gonna get populated when PM peak started, gets the maximum flow, maintains for a while, and coming down, which is basically when we are unloading the network at this point. So the reliability relations are estimated for this simulation results. As you can see here, this is the trajectory-based approach, this is the sub-trajectory approach. And as it can be clearly seen that the linear relation holds much better once we are considering the sub-trajectory approaches. And also, it can be observed that during the AM peak, PM peak, and during the off-peak period, we can conclude that there might be slightly different relations depending on the congestion pattern that we have, congestion distributions. So now the next step is that, okay, so we have the travel time measures and relations here, but how partitioning would impact that. So basically, this is the measures that we have defined to evaluate the clustering approach for different combinations that we are going to talk about. So we applied the snake methodology by Sedmanish and Germanis in 2016, and we used TVN as the measure to assess the impacts of the different clusters. So the lower value of TVN represents a much better clustering approach. So here are the results for different scenarios that we have used. So first of all, we have done different analysis for AM peak, PM peak, and the entire day, AM, PM, and E. Also, we have tried the 2 clusters and 3 clusters. And also, we have tried the directional and the non-directional approaches that I just talked about. So, as you can see, for AM, we have 4 cases, 2 clusters and 3 clusters, directional and non-directional, and we have the same thing for PM and entire day as well. And here the results are shown here. Clearly, in all of them, you can observe that once you move towards the from 2 clusters to 3 clusters, the TVN is improving. So that shows that the 3 clusters has a better characteristics in terms of homogeneity clusters. If we increase the number of clusters to 4 clusters, it is expected to have a lower TVN as well. However, that would make the computational efficiency significantly problematic. So that's why we just stopped at the 3 clusters to just show the applications of the NFD and the impacts on the NFD on the reliability measures estimation. Here we have shown 2 different measures for TVN. One is just the average value over the day, and the other one is just showing the minimum observed TBN over the study period. So here AN peak, here PM peak, here over the entire dates. This is the minimum TBN that is captured, but this is the average over the entire day. And that was one of the interesting thing that we did here in this study in terms of the partitioning. That so instead of partitioning at one particular point, we try to come up with the clusters that would be proper for the entire study time window, which in this case is AM peak, in this case is PM peak, and in this case is the entire day. And this is just one sample of the clusters. As you can see, the kind of really low congested area that is around the network, illustrated by green here, is the sweet profile for that clusters. And then we have the red and blue, which are kind of moderately congested and severely congested clusters have been defined. So this is just showing the clusters for PM peak, the three cluster case, applying the directional approach. So basically this stands for PM, directional, and three clusters. So this is the TBNs associated with this scenario. So now to observe the impacts of the clustering and the reliability relations, you can see here this is the entire network. So basically one cluster case. This is showing the NFD. This is showing the travel time reliability relations for the trajectory-based and the sub-trajectory-based approaches, as you can see here. And now we have three different clusters that we have: the low congested, moderately congested, and heavily congested ones. And as you can see here, they are demonstrating the significant differences with the one cluster case, as you can see. And interestingly, the one cluster is really close to the low congested portion because there are certain parts of the network that are not significantly congested. So basically the behavior at the one cluster is mainly imposed by the low congested scenarios. However, we do have more congested clusters, as can be seen here, with different reliability relations. Which is kind of showing the whole point that the clustering has a significant impact on the travel time reliability measure estimation. And here we have a little bit more results on the directional and the impacts of the reliability measure estimation and the different clusters. And we were trying to figure out how this reliability measures, which characteristics affects the reliability measure estimations more. So once we were trying to figure out that it makes sense that the average density at the different clusters would have a direct relation with the coefficient of reliability. So as you can see, the coefficient of reliability is decreasing in this set of slides, in this set of scenarios over the two clusters and three clusters. So we have defined the clusters in a way to have a decreasing pattern for the coefficient of the reliability, as you can see here. And now we are comparing different elements regarding the density in different clusters. So an increasing pattern is obvious in the average density, and then also an increasing pattern is also obviously can be observed on the standard deviation of density over the clusters. So what we did was, instead of just focusing on average density or standard deviation of density, we tried to look into the density coefficient of variation, which is making much more sense because it's not just about the average density that are different in different clusters, but also what is the standard deviation of densities in those clusters. So both of these measures are important, so we try to combine these two measures together by normalizing the average density by the standard deviation of density. And we observed a really great correlation between the density coefficient of variation and the reliability measures in these different clusters. As you can see, the pattern is almost identical. And that was one of the interesting observations that I made in this study. So with that, I'm going to conclude the first topic. I'm going to speed up a little bit and behind the schedule. So, but I think the first one was a little bit difficult to explaining the different approaches that we had. The later ones are more straightforward. So for emission estimation, the main objective here is to apply a macro emission model based on NFD. And it's not just a function of NFD, but it's also a function of vehicle type composition. And we have developed a nonlinear regression model with a support vector regression model, and we have compared them. So the major approach here is that first we simulate the traffic for multiple scenarios. And by scenarios, they're varying in terms of a little bit in terms of the demand, the day-to-day variations, kind of, and also different characteristics to apply some fluctuations on the scenarios to not have the same NFD all day, all the time. And then we use microscopic for small cases study. We use mesoscopic for larger scale networks. So once we simulate the traffic, then we would be able to apply a microscopic emission model. In this case, we went with the Pennis model, which is a function of velocity and acceleration, as you can see here. And for different vehicle type, diesel, gasoline, LPG, and truck, we would have different coefficients here in terms of the coefficients for velocity or acceleration. So once we do the simulation for different scenarios, we would be able to apply the micro emission models and get the actual emission generated at the network level. Then we have calibrated nonlinear regression model, and we have trained an SVR model to estimate the network level emission based on two factors. One is the NFD or MFD, the network fundamental diagram statistics. And then the other one is based on the traffic composition. So it's not just about how much congestion you do have, it's also about how much emission is generated by those vehicles. So if you have all the network with the electric vehicle, for instance, there won't be any tailpipe emission generated there. So this is an important factor that needs to be considered. And also the NFD, which is showing that if the network is congested or if it is not congested, if the more, what is the accumulation of the vehicles in the network and all of that, they would impact the emission, obviously. And then ultimately, we have simulated some other traffic scenarios to just validate the nonlinear regression model and the train and the SVR trained model to compare how good they're estimating the emission. So here it's kind of a schematic of the approach that I just talked about. So the major thing here is that we have a macro emission model. We have the NFD and traffic composition as the input. So just by knowing the NFD characteristics, which could be at any given time, if you have the average flow or average density at the network level, and if we know what is the traffic composition, how many of which vehicle type we do have at the network level on average, then we would be able to just use the macro emission model that we have developed in this study to get the macro emissions, and we would have the network emission diagram that we are going to talk about at the end. So here's just showing the process that we have the calibration process. We run the traffic simulation, the micro emission models, calculate the emissions, we calibrate the macro emission model, which will be used here, and then we would apply the validation scenarios and compare the macro emission and the micro emission for the validation scenarios. So the macro emission would come from the macro emission model trained here and calibrated here, and the micro emission would just come simply from simulating the validation scenarios, and then we would have the errors that we are going to discuss in the numerical result. For the network, we considered again Chicago network. So this is the CBD that we had in the previous case study as well. We've shown that as a scale. And here, this is the area around it. It is particularly containing the Chicago city. So here we have O'Hare Airport. So if you're familiar with the network, and here we had, I think somewhere around here, we had the Northwestern University in Evanston campus. Sorry, here. Yeah. So somewhere around here, we have the Northwestern University campus in Evanston. So this is the demand profile for one particular scenario. So this is how the demand is changing downtown, and this is how the generated vehicles is changing and the Chicago CBD. So this is defined as Chicago downtown, this is defined as Chicago CBD. And here we are comparing the basically the observed NFD, simulated NFD for these two different networks. So one is focusing on this one is focusing on the entire thing. And you can see they're clearly different pattern. And then we have the nonlinear regression model, and what we observed that in the nonlinear regression model, we tried many different combinations, linear, nonlinear, and this was kind of the best that we could come up with, which kind of making sense as well. So as you can see here, if there is no vehicle on the road, so the density would be 0, the average density in the network would be 0, and the entire emission should be 0. That makes sense. On the other hand, if the network is really super congested and the speed is low, then there would be significant emission, and that's where this constant would play an important role here by multiplying the high density that we have in the network to generate the total emission. And then in between, where we have some vehicles populated, not the 0 speed, but the reduction in the speed by increasing the density, we would have both increasing density and decreasing the speed playing an important role in defining the emission rate. Here are for the two pollutants that we have, for the two networks that we have estimated different models that can be used as the macro model. Note that for the CBD area, we just use the microscopic approach, and for the Chicago's downtown or city, we just use the mesoscopic approach for simulating the scenarios. Obviously, the mesoscopic approach, there would be some approximations in estimating the emission related to the microscopic approach, but there is no way that we can apply the microscopic approach for the larger scale networks. That's why we wanted to have both of them and show the errors at both levels, basically. So here, to demonstrate how significant the different scenarios that we had were different, so we consider 10 traffic scenarios for the calibration and 3 traffic scenarios for validation. As you can see, different characteristics of the networks are varying different significantly. The maximum average density, as you can see here, is changing. One is for the CBD, one for the city network, as you can see here. And then the average, the maximum average flow, is compared here in different scenarios. As you can see, they are significantly different. And also the area of hysteresis loop in the NFD shape, in the observed NFD compared here. And then ultimately here we have the impacts of the different traffic compositions in terms of the 4 different vehicle types that we would have. We apply different scenarios, and we apply them randomly to different vehicles. The vehicle type, we allocate the vehicle types to different vehicle types randomly. And you can see this, there is significant fluctuations in the emission rates. For one particular traffic scenario here, you see significant variations. The results demonstrate that the average error is less than 10%, kind of acceptable, and SVR model is doing much better than the nonlinear model. However, even the nonlinear model, they might be around percent. For the SVR method, it was below 5%. Obviously, the SVR models outperforming the linear model, the nonlinear emission model. And here is the network-wide emission diagram. As you can see here, one thing that should be noted here in this diagram, we are showing the emission rates. It's not the total emission that is demonstrated there. And having lower emission rates here by itself, it doesn't mean that situations is becoming much better. You know, it could be that you have much more emission overall, because the emission rate might come down because the speeds are coming down, but the vehicles would be on the road for longer time because now the output rate of the network is dropping as well. Basically, the flow rate, correct, is dropping. So the vehicles would be on the road for longer time as well. So the total emission would be generated would be higher. So although we are observing a reduction in the emission rates, but since that lower emission rates would generated for a longer time, so overall more pollution would be generated. That needs to be considered. And so here we have the actual NED observed, which is a 3D diagrams that we have defined. For every 5 minutes, we have the average flow and average density for the network, and we have the generated emission during that 5 minutes as well. So we have drawn this network, this diagram here. And here you can see this is how emission rate is changing versus the density and how emission is changing versus flow. And as you can see, there is no function, basically because of the hysteresis phenomena that we have in our network. So with that, I'm gonna move to the CAVs application. So here, the major features that we are gonna consider in our studies, the heterogeneous drivers and AV that are spatially and temporally varying distribution over the network. We are kind of gonna consider capacity variations at intersections. In addition to the freeways, we are going to talk about the arterials as well, and mainly we are going to consider the en route strategy for CAVs as well as a key factor in comparing the different market share penetrations. So the approach here is that, so first we have some calibrated microscopic models from the literature mainly for AVs, one model for AVs, multiple models for RVs and CVs, consider the heterogeneity of the drivers. And then once we have these microscopic models, we have come up with macroscopic models associated with these microscopic models, assuming that all 100% of the drivers or vehicle types are the same. So we have multiple microscopic models here. So for each of those microscopic models, assuming that the entire traffic mix is one of those particular vehicle type and driver types, we have come up with the macroscopic models. And then we have modified our Mesoscopic Simulation tool using those macroscopic models. However, in a typical Mesoscopic Simulation tool, the macroscopic model, for example, the modified green shows would be applied for the link is just one model. Now we have multiple models, and these different models apply for different vehicle types. So depending on the proportion of the different vehicle types that we have at any given time on particular links, then we are gonna calculate an average model kind of between these macroscopic models, find a speed that would result in an average spacing that would give us the same density that we have based on the number of vehicles that we have on that link. So that's kind of the major modification that we have done for the freeway portion. And then here we also modify the intersection capacity and also the arterial models, but due to the lack of the data in the arterials and also the intersections, what we have done, we have come up with some proportional-based adjustment factors that are defined based on the comparison of the freeway models for different proportion of the vehicles of the CAVs or regular vehicles. And ultimately, we have assessed the impacts of the different market penetration rates by the NFD and show that how the different penetration rates of CAVs affects the NFD. So for micro simulation for vehicles with no communication, we have just used the model presented by Hamner et al. In 2015, but we have considered the heterogeneity among the drivers, as I mentioned earlier. So we have defined different microscopic models for different driver types. And also for V2V, since we don't have any data, but to kind of capture the impacts of the connectivity, instead of using the Hamner et al. Model, we use the IBM model, which is more deterministic models. So we assume that the more information we have, the stochasticity would reduce. So it makes sense to use IBM models for connected vehicles. And again, we have calibrated that for different vehicle types. And for the autonomous vehicles, we just use one simple model that presented by Talcott et al. In 2016. So based on those three types of models that we talked about, we have three different spacing relations and speed relation, as you can see here. Here we have just simple reaction time multiplied by the speed, which gives us the spacing for autonomous vehicles. And then we have two different models for RVs and CVs. And also each of these stands for different models for heterogeneous drivers that we have. And basically, as I mentioned, the speed and different proportion of the vehicles. So we have different vehicles that belong to different vehicle types at different links, and they would have different spacing on the link based on the speed that they would have. So we can calculate the weighted average of the spacing, and that weighted average of spacing, the inverse of it would be correlated with the density at the link. And that's how we come up with the macroscopic approach. So here, the macroscopic models are presented for the different type of users, as you can see. So the autonomous vehicles is just one red, and for connected and human one, the blue and green, we have multiple diagrams, as you can see there. We just use a triangular model, simple triangular model here for the autonomous vehicles. For the other ones, it's a little bit more different from the triangular, but it's almost like triangular models. They are different. And obviously, the blue lines are overall higher than the green one. However, as you can see, it doesn't mean necessarily that all the users type of the connected vehicles would better off all user type of human-driven, because we have the heterogeneity of the performance, so it depends on the driver type as well. It's not just about having connected vehicles or connectivity available or not. And then ultimately, for the mesoscopic simulation, as I mentioned, we use the kind of average mesoscopic model, average macroscopic model for the mesoscopic approach for the freeways. For the arterials and intersections, we just simply use the adjustment factors that we have to load based on the relations that we observe on the freeway and the maximum flow rate mainly. So here is again the explanation on how the mesoscopic simulation works. So at any given time and for any given link, we know the different vehicle types that we have on that link at that time. So basically, we know the number of vehicles divided by the lane length that would give us the density. And then we would try to find the average speed that would give us the average spacing, where the spacing is calculated for different vehicle types on that link. That would give us the same average spacing, that the inverse of it would be equal to the density. So to solve this nonlinear problem, we apply the golden section methods, and we have solved it, and we have simulated the traffic. So again, similar to the previous, we have considered the Chicago City or downtown network for simulation. Here we have considered 5 to 10 a.m. and around 800,000 vehicles have been simulated. We have assumed in the base case scenario, 25% of the vehicles have access to en route travel time information, but we assumed all the CAVs would automatically, if a vehicle is connected to autonomous vehicles, they would have access to the en route information. Based on that, we have been able to simulate the traffic with the modified tool that we had, and we have been able to compare different scenarios, different market penetration rates. So here on the right side, we have the kind of 100% scenario. So 100% AV is the blue one, 100% connected vehicles is the orange one, 100% RVs is the regular vehicles. So you can see there, this is a really highly congested scenarios that we have tried. So you can see there is a significant hysteresis loop here. And as we increase the connectivity and information, the hysteresis loop is decreasing significantly. Here we are keeping the RVs at 25%, and here we are keeping RVs at 75%, and we are just switching the AV and CVs and see which one would be more effective. And as you can see here, there's not much difference when the dominant number of vehicles that you have in the network are regular vehicles. There is not much difference between connected vehicles and autonomous vehicles. However, once you do not have much RVs left in the network, there would be more significant variations between the connected vehicles and autonomous vehicles as the options that you can provide there. So basically what you can see here as the remaining portion is kind of showing the gridlock in the network, right? So this is at the end of the simulation, the vehicles that have not been able to get to their, have not been able to leave the network. And here, in this case, we do not have any gridlock at all. So all the vehicles were able to leave the network at the end. Here it's kind of showing a mixed approach that we have three kind of portion of the vehicles and see the impacts of the based on the NFD. So here we are showing, I think this is the last main slide that I have, and after that I'm going to sorry, more than 45 minutes. Here we are applying different strategies of the connectivity, different features that we considered in our modified simulation tool, which basically modified DYNASMART. So we are showing the different features impacts one by one, and it's kind of a cumulative one. So A, we are considering one feature here, and B, we have added another feature. And C, we have added a feature to B, and D, we have added a feature to C. So it's kind of a cumulative features that have been added, and this is the ultimate tool that we have. So in the first one is that we are just considering the impacts of the en route user. So basically, this is the same DYNASMART tool without any modification. The only thing that you're changing is the percentage of the en route users. And as you can see, there is a significant differences between the basic scenario and the scenario with the connectivity and automation. The connectivity and automation are top of each other because there is no difference between the connected and autonomous in this case, because they both would have access to the en route information. Now here we have added the adaptive traffic flow models on the freeway links. As you can see clearly, there is a significant shift between the autonomous vehicles and connected vehicles now can be observed. However, it's not that significant, and the main reason is that in the network that we had, as you can see, the blue lines are the freeways. Most of the links are the arterial, so there is not much freeway available there. So it is expected that all alone, we would not observe much impact of the modification to the simulation tool. Once we apply the arterial links, you can see the differences between the red and blue is more significant here. We have also adjusted the arterial links models based on the freeway models that we have as the comparison. And then ultimately, once we apply the intersection, you can see there is a much improvement can be gained. And also there's a much significant difference between connected ones and autonomous ones. They're here. So with that and the conclusions, we showed the applications of the NFD and different applications like the travel time reliability analysis. We showed that how network partitioning plays an important role there. We showed that how we can use NFD to estimate a macroscopic model for emission, considering the dynamics of the network. And also we showed how we can use NFD to assess the impacts of the connected and autonomous vehicles at the network level. And for the future research directions, which kind of main reason that I included these three together is that, so first of all, we need to still have data-driven approaches for arterials to modify the models that we talked about. So instead of just going with the adjustment factors that we have developed, we can use the data-driven approaches, which we call new source of data, basically, on the arterials, with and without connected non-autonomous vehicles. Also, we would like to consider the impacts of the CAVs on the travel demand as well. So what we showed here was that, okay, the demand is fixed, the vehicle type and vehicle combinations are different, how the scenarios would look like. But obviously, if you reduce the congestion, there would be more people willing to use the roadways because there is less congested. So there would be some demand following up on that. And also, if you now have an autonomous vehicle that you're not driving yourself, you are willing to make more trips as well because you're not driving, you have reduced value of time, kind That's also another important factor that needs to be considered in future research. But the last two, which are my favorite ones, are to apply the perimeter control strategies and see how the perimeter control strategies and the clusters would change the network travel time reliability measures. So obviously we expect that there would be significant improvement there, but it's good to be studied. And also how to apply the NED concept that we talked about for the perimeter control strategies. Another interesting topic for the future research. And here are my great collaborators. Obviously, I'm honored and my pleasure to be a student of Hani Mahmoud's group. And I've learned a lot and will do in the future as well. For the travel time reliability and the clustering, Nicholas and Mohammad Reza from Said Manish from EPFL, they helped us a lot. And Miyad is my dear friend. We have worked on the NFD concepts and multiple papers together. And Ali Reza helped us with the micro simulation portion of the connected and autonomous vehicles. And my dear colleagues at MSU, which without them, this research were not possible at all. Specifically, Fatima, I think, should be in this call as well. So for her great work on the connected and autonomous vehicles and modifying DYNASMART. And these are the three publications that are all happening in 2020 for each of the topics that I covered. And that, I'm going to stop. Sorry it took longer than what I expected. I think I was not paying attention to the time in the first one and spent lots of time on that one. Sorry about that.
It's totally fine. Thank you for your interesting presentation, Ali. So we are now open for questions. Please feel free to unmute yourself and ask any questions. So I'll go first. I have a few questions. You can go back to slide 23.
Cannot see the slide numbers. Oh, yeah.
Yeah, it's...
Okay.
So you show some MFDs there on the top row. So
yeah.
Are those the MFDs for the whole network or like clusters?
So first of all, there are NFDs of the peak period. So I think they're PM peak. So just that's why we are observing a really period short changes basically there. And the first one, the first column here, right, for NFDs and reliability relations is where you have just one cluster. So it's one network for the entire network. Then I should have explained that better. Sorry about that. So, and then the second column here is for these are the three clusters that we have.
Three different clusters.
This is cluster 1, this is cluster 2, this is cluster 3. So in a way, you can say the average of cluster 1, 2, and 3 would give you this. Right? So the average of these three would be equal to this one. And as you can see, there is much similarity between this one and the first cluster because the first cluster has the largest size. So obviously the average would be closer to the one that has the largest.
So another question about your the second part. Do you use for the emissions estimation only one MFD for the whole network?
So actually, as you can see here, so we had different observed NFDs for the whole network.
So for each simulation, you derive the MFDs like a different MFD.
Yes, exactly. Observed NFD, basically. Simulated NFD, not observed. So we simulated different NFDs for each scenario. And then, so the NFD was different, but also in addition to NFD, we had tried different vehicle combinations to generate the emissions, right? So if all of the vehicles were, for example, diesel or all of them were gasoline, then the emission would be different, the emission rate, right? So for the calibration process, we had 10 different NFDs, basically. And you can see the features of them, how are different. So here is the maximum density, how it is changing between 140 to 170. This is the maximum average flow observed in different scenarios. And this is the area of hysteresis loop that is changing over the different scenarios. And then, so we simulated all these different scenarios, and then we simulated different micro emission models for the traffic compositions as well. And that gave us the huge data sets that we use to calibrate the macro models.
So demand was for 24 hours, just one day, right?
I think the demand, I think I mentioned, should be just, yes, it is just the AM peak. So it's
It's
just
just AM peak.
300 minutes. It's about 6 hours.
I have a couple of quick questions. My name is Bahir Abdul Hai from UFT, University of Toronto. If you could go back to slide 19.
19?
Yeah.
Okay.
On the top right, you have, I don't understand the MFD there. It's peaking at flow of about 4,000, then at density around 20, it dips and then goes back up and dips at a much higher density. And you mentioned like one was afternoon peak and one evening peak. I didn't get that.
No,
Shouldn't it be one MFD?
So basically, this is the observed and simulated NFD. So basically, we're calculating the average flow and the average density every 5 minutes, right? And we are just showing the data points associated with every 5 minutes, right? So this is early morning here, right? So you have a really flow up at the network, you have a really low density. So if you want to talk about the basically the NFD existence of one NFD for the network, right? So if you kind of continue from here, right? So if you do not do any unloading, right? If you continue loading, so basically your NFD would continue something like that, most likely. So what has happened here, so every 5 minutes, the network is getting more congested. It is AM peak, right? The flow is increasing and the density is also increasing. And then at some point around here, then the network starts unloading. And that's why the flow and also the densities start decreasing. And then after the offloading for a certain amount of time, which is basically here, then you're gonna start loading the network again, as you can see, right?
Okay, so the dip in the middle is like because of the offloading in between the peaks.
Exactly.
Okay, the second question, thank you. The second question on slide 39.
39.
Okay, now it seems to me that you're estimating a macro model based on what you get from micro models. And the left diagram, for instance, shows that if you have AVs, you get capacities that are much, much higher than regular human driver. So if I read into this figure, so let's say, for instance, human drivers give you a capacity of about 2,000 vehicles per hour, while autonomous gives you up to 3,000 or so, because you're driving this from a micro model, deriving this from a micro model. But if you simulate traffic on an urban freeway, similar to the case studies that you've showed later, which is very congested during the peak with back-to-back on-ramps and multiple bottlenecks, 100% EVs will not give you that much increase in throughput. So, for example, if you plot fundamental diagram for the freeway or for a spot on the freeway, you'll see that it's peaking at 1,800, 1,900 vehicles per hour per lane for regular driving. For 100% AVs, it's going to be like 22, 23, which is not that significant difference as we think we will get from autonomous vehicles on the network. And then, so what I'm trying to say here is that you might be overestimating the benefits of AVs. And if you're taking this and generalizing over the network, then again, you're overestimating the benefits of AVs all over the place. So this is like my feeling. I'm not sure what you think of it.
Yeah, I think the point that you're making here is completely valid and true. But there is one important factor that needs to be considered in that. So all those bottlenecks that you talked about, they are captured in the mesoscopic simulation that we are applying that. This is just the macroscopic model that is used in the mesoscopic approach to move the vehicles, right? So for that, so basically, so let's focus on the autonomous vehicle. So this point here is coming from as assuming 1 second of reaction time. So if you assume 1 second of the reaction time, then the maximum flow rate that you would get would be around this number. So basically, this is assuming that there is no bottleneck, correct? You have freeway, unlimited, and the only vehicles that you have on the road, they are all 100% AVs. If they can all maintain 1 second's headway, 1 second's reaction time, then the headway would be around 1 second as well, a little bit less than that. And then what you would gain would be that high capacity that you can see here, right? And that's that's kind of a valid assumption, right? But this model will go inside to the mesoscopic model. It's going to be mixed with other vehicle types, because if you have different type of vehicles, but if you have even 100% AVs, still there is going to be congestion. There is going to be intersections. There is going to be signalized intersection, four-way stop ways,
or on ramps on the freeway,
and the ramps on the freeway, and all of that. So because of that, there is going to be congestion, and you are not going to observe that high at the network level, obviously. So this
but if you in the micro model, let's say focus on a freeway with on ramps and so on. So it's not that infinite homogeneous pipe, but rather you have on ramps every now and then. What you will get is a fundamental diagram that would peak at much less than that, 2300 or so, and then start going down.
Yes, you're absolutely right. But the key point here is that once you add the ramps, then you are not talking about links. It's a network.
Yeah.
It's a small network, but it still is a network, right? So here we are focusing on the microscopic model, right? Again, unlimited, non-interrupted flow. This is the macroscopic model associated with that microscopic model. But ultimately, once we are using these macroscopic models into our mesoscopic simulation tool, then the bottleneck, then the feedback of the queues and everything from one link to another link, they would come and make a roll and would reduce the maximum flow rate significantly. And as you can see on the results as we got here, correct, the flow rate that you are estimating for the network is around 500, 600, you can see. But some part of it is because it is averaged over all the links, and not all the links are at the maximum. But I'm 100% sure that if we just on the links that are having high flow, if we just calculate those average numbers, we are not going to observe the this much of 3,000 vehicle per hour in the network. There's no way, because congestion.
Yeah, I like your point about that. Now once you add the ramps, then now you're talking about an NFD, not a fundamental diagram at a point. Okay, thank you.
Thanks for the great question.
Hi, Ali. I have a question.
Sure.
I apologize if they asked it already because I got disconnected, but I saw you showed some pictures showing the standard deviation and the travel time, right? And now those standard deviations are huge compared to the travel time. So I'm wondering what's going on. So you see, the standard deviation is like 2 or 3 times the mean travel. Well, that's the pace, right?
Yep.
Yeah. So I'm wondering, because that's really unusual to have such high coefficients of variation, standard deviation divided by the mean. So I wonder if you look at those.
So actually, these are what we have observed at the network level, and it kind of shows that how heterogeneous our network is. And that's why when we do the network partitioning, that helps and that makes the numbers that improves the estimation of the reliability measures. So as let's go back to the, yeah, I would like to. So basically those factors that we're talking about here, correct?
Mm-hmm.
So these measures here, correct? So here it's the 6 on average for the, I think this is for the PM peak, correct? What we were seeing there, it was the entire network, entire day. Now here it's for the PM peak. So that number is 6 times, kind of. As you can see, for certain subnetworks, right, for the clusters.
Wait, but hold on there. So 6 times, if it's a coefficient of variation, right, the sigma divided by mu, basically, right?
It is, yeah.
So that is almost non-physical. It's like a chaotic system, chaos.
So that's exactly my point. So as you can see, this 6 is reduced to almost 2 for the congested portion. So
Right,
these
but
2 are the congested cluster, and this
even
is kind
2
of
is
the
really high.
non-congested clusters, where you do have significant variations because there are not congested. There are vehicles traveling around. Significant variations can be observed.
Right, but it just doesn't make because look, if you have a normal random variable, coefficient of variation of 30%, so 0.3 would give values that could be negative, right? So travel time tends to be normal. Maybe it's not in your case clearly, because with that 2, you would get a huge spread. So there's and are these values common in the literature?
Yeah, I think the results that we got was consistent with the previous studies. But one thing that you need to pay attention here is that these are not the travel time. They're travel time per unit of distance.
Yeah, but still.
So maybe that's a reason that we are observing such factors.
No, I don't. No, I think it's better to do it, like that, per unit distance. But yeah, it strikes me as it's too high for me. I mean, did you plot a histogram of these travel times? Because it's not going to be normal if it's like that. It's maybe a power law. That would be surprising. Power laws that have these type of coefficient of variations, right? But typically those orders of magnitude are for other random variables, such as, stock prices or population, cities, whatnot. But travel time to me is kind of striking. So.
But
All right.
I will look into it. It's a great point. So I will try to get the histogram of it. I didn't try that,
Yeah, in engineering, you seldom come across coefficient of variations that are greater than 1. The exponential distribution has a coefficient of variation equal to 1, so that gives you an idea of the type of chaos that it's in the data. Another point I had is with the emission modeling. So you showed the relationship between emissions and density or flow. And then, there's a hysteresis. Sorry if you explained it already, but what is the reason for that?
You mean for this?
Yeah, the hysteresis loop. So at a given density, you have 2 emissions, right?
Yeah. So the reason is because we are unloading the network, right? So basically here how it goes. So up to this point, which the density is increasing, we have the loading phase. So basically this is where the network has kind of flow breakdown has happened, right? So you get to the maximum flow, you maintain it for a while, and then ultimately the gridlock happens, and then the flow breakdown happens, and then the density would increase and the flow would decrease. And then at this point, we have started unloading. As you can see, there's a significant jump here as well because it starts unloading. And then the flow would come down and density would come down as well.
Right. So I understand the hysteresis in the flow density plane, but not in the emissions density plane.
So again, this is not accumulative emission. This is the emission rate, right? And the emission rate depends on the speed. So once the speed of the vehicles slow down, right? So the emission rate would decrease as well because it is directly correlated with the speed. And also, once the density is decreasing, that would decrease the emission rate as well.
All right. So there's a hysteresis.
This is again emission rate. It's not the accumulated emission.
Yeah. No, that's fine. That's fine. The reason is because there's hysteresis in the speed density maybe diagram because the loading and unloading of the network.
Exactly.
Okay, that makes sense. All right. Thanks very much.
Thank you. Thank you for the great point that you made. I will look into it, but yeah, it's interesting. Now you pointed out that coefficient of variation is larger than 1. It might be.
Yeah.
It's suspicious. I will take a look into it. So.
All right. Thanks so much.
Thank you.
All right. So I guess we've gone long overboard. Rafa, you want to thank the speaker and all the audience?
So yeah, I think we don't have any more questions. So thank you again, Ali, for your presentation, and thanks to everybody who joined us today. We'll have another webinar next week at the same time, Friday, 11 a.m. Eastern time.
Let's start with this. How many people are planning on recruiting any master students from the list where you're going to pay? Right. So if that's the case.
Thank you, Rafa.
Yeah, I do. So yeah, thank you again, everybody. See you next week.
Thanks. Bye.
Bye.